Hello, and thank you for joining us for the SLW Institute webinar, Digital Twins, Transforming Decision-Making for the Future. A recording of this webinar and the slides will be made available to all registrants. Feel free to enter any questions using the Q&A feature in the Zoom menu. We invite you to follow us on LinkedIn to see news about other upcoming webinars. And with that, I'll turn things over to our moderator.
Hey, thank you, Michelle, and welcome everybody to our Digital Twin webinar today. This one is particularly fascinating for me because I'm not that familiar with digital twins or how highly advanced this whole process and organization around them has become in recent years. So today we're very fortunate to have two highly expert speakers to talk about digital twins. And the first one I'll introduce is Dan Isaacs, who's with the CTO of the Digital Twin Consortium and the VP Technical Director of Object Management Group. Dan is currently setting the technical direction for the member consortium and liaison partnership and business development support for new memberships at the Digital Twin Consortium. Previously, he was a director of strategic marketing and business development at Xilinx, where he was responsible for emerging technologies, including AI, machine learning, including defining and executing the ecosystem strategy for the industrial IoT group there. And prior to joining the Digital Twin Consortium, Dan was responsible for automotive business development focused on automated driving and ADAS systems. So Dan represented Xilinx to the Industrial Internet Consortium, and he has more than 25 years of experience working in automotive, military, aerospace, consumer-based companies, including Ford, NEC, LSI Logic, and Hughes Aircraft. So we're very lucky to have Dan with us today, and I've previewed his presentation. It's really fantastic. And another speaker that we've all enjoyed having on prior webinars is Manjeet Rege, who's a PhD in AI, and he's director of the Center of Applied Artificial Intelligence and chair at the University of St. Thomas graduate programs in software engineering and data science. So we welcome Manjeet to our program today. And Steve Komarec is another presenter today. He's a principal at the firm here. Steve's an accomplished patent attorney who does a lot of work in the mechanical art area, and it was his brainchild to put this webinar on today. So we thank Steve. Steve will also get into some of the legal aspects after we explore the technical aspects. Suneel Arora, another principal here at the firm, is also one of our panelists today, and Suneel's going to be asking questions of the speakers as we go forward. So with that, let's get it rolling. We'll go straight to Manjeet to get this webinar started.
Hey, thanks, Steve, and thank you everyone for joining us. Let me start off with talking about why are we talking about the digital twin market. So the convergence of emerging technologies like AI, IoT, and the big data is driving the adoption of digital twins across industries to build products, monitor assets, optimize maintenance, and reduce downtime. The rapidly expanding digital twin market indicates that while the digital twins are already in use across many industries, the demand for digital twins will continue to escalate for some time. Now, last year in 2020, the digital twin market was valued at about $3 to $5 billion. And some industry analysts speculate that it would continue to rise sharply until at least 2027, climbing to an estimated $50 billion. So the machine and equipment health monitoring segment is poised to capture over 30% of that market share by 2027. And the increasing need to reduce asset downtime, to improve the performance of different products, and quicken fault diagnosis is the major driving factor. The Europe digital twin market size is expected to generate a revenue above 10 billion by 2027. And this is due to the presence of leading players such as PTC Incorporate, Wipro, and Schneider Electric, and their hefty investment in R&D. Let me now define what a digital twin is, now that we have talked about the importance of it. And this can be quite a mouthful. So a digital twin is a dynamic virtual representation of a physical object or system, usually across multiple stages of its life cycle. It uses real-world data, simulation, or machine learning models combined with data analysis to enable understanding, learning, and reasoning. Digital twins can be used to answer what-if questions and should be able to also present the insights in an intuitive way. So a digital twin is a virtual model designed to accurately reflect a physical object. The object being studied could be, for example, a wind turbine, which could be outfitted with various sensors related to vital areas of functionality. And these sensors will produce data about different aspects of the physical object's performance, such as energy output, temperature, weather conditions, and more. This data is then relayed to a processing system and applied to the digital copy. So once informed with such data, the virtual model can be used to run simulations, study performance issues, and generate possible improvements, all with the goal of generating valuable insights, which can then be applied back to the original physical object. Now, let me talk about the high-level component view of the digital twin. So as the diagram shows, the data underpins the twins. The representation of the real world is key to modeling the real world. The sensor data provides the current state of the real world, and the modeling output is generated by simulations. Managing this data is very important to ensure that a set of output data can be traced back to both the system configuration at the time and back to the initial conditions if required. Simulations can generate huge amounts of data and more data than possibly what real world data can generate via IoT devices. So dealing with such volumes of data, so that management of data is extremely important. It is vital to note that a digital twin does not stand alone. It must be integrated with the overall enterprise architecture. As a matter of fact, some elements that are used in the digital twin are likely to already exist within the organization, and they can be extended or repurposed to support the digital twin models. Let me talk about using the digital twins to solve real world problems. So they can be used to address various problems that organizations face, including but not limited to. I'll not get into all of these, but let's talk about project planning. A project planning digital twin can be used to compare different life cycle plans based on impact from other twins as they evolve to assist with, let's say, contingency or resilience management to ensure the plan is achievable. In terms of even capturing requirements, a twin can ensure that the requirements are captured during the earliest stages of the life cycle of a product, and that the life cycle are maintained, verified, and validated as the overall life cycle evolves. Also, in terms of real-time decision making, a twin can allow decision makers to rapidly understand the implications of any changes that are made to an asset at any point in its life cycle. For example, if a material change is made, what will the impact be on the project plan model, the design model for mass and center of gravity, the cost model for overall financial impact, and so on and so forth. Let me talk about the advantages and benefits of digital twins. First, for better R&D. The use of digital twins enables more effective research and design of products. With an abundance of data created about likely performance outcomes, so that information can lead to insights that help companies make needed refinements to their own products. And this is before starting production. Greater efficiency. So even after a new product has gone into production, a digital twin can help mirror and monitor systems with an eye to achieve and maintain peak efficiency throughout the entire manufacturing process. And finally, the product end of life. A digital twin can help manufacturers decide what to do with products that reach the end of their own life cycle, and let's say need to receive final processing through recycling or other measures. So by using digital twins, they can determine which product materials can be harvested. Now, when should you use a digital twin? While they are priced at what they offer, their use isn't warranted for every manufacturer or every industry. Not every object is complex enough to need the intense, regular flow of sensor data that the digital twins require. Nor is it always worth it from a financial standpoint to invest significant resources in the in this entire endeavor. So on the other hand, numerous types of projects do specifically benefit from the use of a digital twin model. For example, physically large objects, think about buildings, bridges, other complex structures bound by strict rules of engineering. Mechanically complex projects such as jet turbines and aircrafts, power equipment that includes both mechanisms for generating power and transmitting it, manufacturing projects. So the industries that achieve the greatest success with a digital twin are those involved with large scale products or projects such as engineering, automobile manufacturing, aircraft production, rail car design, building construction, manufacturing, and things of that nature. So what are the things we should be considering? While the digital twins allow us to carry out simulations at multiple points in the product life cycle to improve decision making, we need to understand the business value and the impact of creating digital twins before we invest a great deal of time and money. I think we must first answer a simple question. Why are we doing this? Sometimes the answer could be obvious: to reduce project costs, get a product to market faster, to achieve regulatory compliance. But in other instances, the value is not so clear. So three considerations that we look at are the complexity, that is how expensive will it be to create a digital twin, breadth, that is how generic or how specific will the digital twin be, and third, the depth, how detailed and accurate will the results of the digital twin be. In reality, due to the wide variety of problems that the twins can address and due to the trade-offs that are inherent in each problem, it is likely that you'll end up with multiple federated digital twins that work together. So it may not be one single digital twin, but a number of these federated work together. And you'll hear more about that later from Dan Isaacs as well. Let me talk about a few use cases, a few applications of the digital twins. Manufacturing is the area where rollouts of digital twins are probably the furthest along, with factories already using twins to simulate their processes. So in this particular case study that I have cited here, an industrial manufacturer was facing numerous quality issues in the field, resulting in costly maintenance and high warranty liability. So to address these problems, its engineering and supply network organizations issued, or rather pursued, a digital twin approach. So first, they combined the as designed bill of materials with all of the analogous information produced during manufacturing, including procured parts, details, and assembly details. So that step allowed them to run analytics and glean insights into different issues that were affecting quality. So as a result, the team was able to improve the assembly process, reducing rework by 15 to 20%. So that was manufacturing. New car development mostly takes place in a virtual environment. The overall, the twin model of a car comprises of software, mechanics, electrics, and physical behavior. So this allows to simulate and validate each step of the development in order to identify problems and possible failures before producing the real parts. And as we are getting, more and more smarter cars and cars embedded with more sensors, we'll see more of that as well. Finally, with the world going wireless and embracing wearables, we could run hospitals like smart factories. Wireless sensors and data analytics will help correctly diagnose patients in the ambulance. It will allow us to administer correct treatment faster, which could lead to faster discharge from a medical facility. It will also allow us to monitor people remotely from home. So in this example that I have cited here, GE is looking at patient monitoring. They're building wireless tools that could one day be no larger than a Band-Aid and constantly stream heartbeat, blood pressure, respiration, and other information into the cloud, where software can analyze it, alert doctors to anomalies and looming crises, and effectively then go and create a digital twin as well. So all of this will, of course, help improve care and cost. So to summarize, a digital twin is a computer program that takes real-world data about a physical object or system as inputs and produces as outputs simulations of how that physical object or system will be affected by those inputs. With that, I will hand it over to our next speaker, Dan Isaacs.
Great, thank you, Manjeet. And thank you everybody for attending and providing me this opportunity to give you an understanding of digital twin with some very specific examples that highlight the value and the transformative business outcome recognized through using a digital twin. My name is Dan Isaacs. I'm the CTO of the Digital Twin Consortium. Next, please. And also aligned with this, why is this getting such a focus and understanding, looking at this going from single digits back in 2019, 2020 in terms of the forecast up to here, seeing this growth rate of over 35%. And in fact, there is a publication that just came out. Well, it was published in April of 2021 from Grandview Research, where they were showing the market size in 2021 was estimated a little over 7 billion. And the revenue forecast for 2028 is actually over 80 billion. So you're seeing a cumulative annual growth rate of over 40% during this period. So what's really driving it? You saw some examples from Manjeet. Why don't we take a look at the next slide, please? There's very specific challenges in the market space right now for digital twin. There's limited interoperability. There's market confusion. If you ask 10 different people, what is a digital twin? You'll get 10 different answers. In fact, I was talking to a customer and said, no, you're not going to get 10, you're going to get 20, because within my organization, a digital twin means something very different to each different area. And so really trying to cut through that confusion in terms of what is a digital twin, what is a minimally viable digital twin. And then also look at it from a standpoint, in fact, one of the analysts came out, when artificial intelligence was just starting out, everybody became an artificial intelligence company or expert. We saw this in the communication side. We're seeing it now with the digital twin. One of the analysts coined the term twin washing. So really, what does that mean? And how can you understand that? And look at that from the overall stakes involved, right? It is a journey, but if you get that right and you invest in that and you understand how to go and take that approach, the payoff is absolutely worth the risk, as you'll see in some of the examples I'll show. Next slide, please. So where does the consortium come in? It comes in to look at ways through the collaborative and best practices, understanding the capabilities across the different areas and spectrums and focus of a digital twin, where it affects it, how to improve that interoperability, how to accelerate not just the awareness, but also the adoption of digital twins, and through very concrete examples, demonstrate that value recognized. Next slide. Next, please. Thank you. So a little bit about the consortium. We were formed back in middle of May in last year. We had both a combination of researchers, of users, so end users, as well as technology providers in academia and government, as a combination of membership in terms of joining with the consortium. Next slide. You can see here when we started out, we actually had 4 founders, and that was Microsoft, Dell, as well as ANSYS, physics-based modeling, simulation and modeling company, and also a multi-billion-dollar property management and construction company called Lendlease, based out of Australia. And as we grew, more companies came involved that we were already in discussions with. So GE Digital came in, Northrop Grumman came in, and then we had Bentley and Autodesk joining us. So now we have 8 members. In fact, just yesterday, press release went out, was issued by Johnson Controls. Johnson Controls has now joined the Digital Twin Consortium as a main contributor. And you can see we had about 50 members, what we called our groundbreakers at the beginning. We are now over 250 members and continuing to grow, which is the fastest growing consortium under the Object Management Group, our umbrella organization. Next slide, please. Next, thank you. So a little bit about the vision and the mission, really to become and have that authoritative voice in terms of digital twin and digital twin enabling technology as it relates to policy, security, trustworthiness, interop, and overall development. And through the collective best practices, the depth and breadth and expertise, as you saw from not only our founders and contributors, steering committee, and our members, but bringing that all together in this collaborative effort so we can now have a common vernacular, we can speak the same language and understand what we mean within the consortium, and then extend that out into communities of like interest and help to cut through that market confusion. So with the definition, we have published a complete definition and glossary that allows it provides the framework and the understanding overall of what a digital twin is, where you're talking about a virtual representation of a physical entity and or process that has a level of synchronization of data at a given frequency, it's called a twinning rate, and a given level of fidelity. And that really talks about the dimensions of that interconnectedness of having that data being able to provide you the relationship between and the understanding of the physical entity and or process back to your virtual representation. So publishing statements, opinions, partnering with industry, academia, and government, really to drive, as I said, not just the awareness, but also the adoption through different use cases and implementations that will take what the expected outcomes are and look at that in the context of what was actually realized. What did we learn from that? Were the expectations met by the actual outcomes, and what type of guidance can be provided through that, as well as were there surprises and what were the challenges and how were those addressed? So really bringing that forward in terms of a use case and a reference library, that's continuing to drive out. So we have several different initiatives. I'll talk about those at the end of the presentation, but really to help to propel, to push this forward in terms of the innovation and the thought leadership that's been demonstrated and accelerate the market. Next slide, please. The structure of the Digital Twin Consortium is around different domains. So we have working groups focused on aerospace and defense. And we're not just talking about the planes or the ships or the land vehicles. We're also talking about things like DevSecOps and cybersecurity and protection from that standpoint. We're also looking at different aspects of how the digital twin can enable in these different areas. We just had a great session yesterday where we had over 120 folks coming in, and we had joint roundtables and discussions around that. So bringing that, again, that collective knowledge and thought leadership, bringing that through. FinTech, so this is one of our newest working groups, is understanding smart financials and the relationships of digital twins. So not just about smart contracts and securing the payments, but also in terms of our transactions, but looking at it from the very initiation all the way through the execution of those. Healthcare and life science, as you just saw from Manjeet, digital twin of the self, but not simply that, also looking at, and a perfect example is where we are right now with this pandemic, is how can we break down the silos between the big pharma and the healthcare providers and provide that information that's so desperately needed by the community. So looking at those different aspects. Also in terms of manufacturing. And again, this isn't just about the manufacturing the asset itself, but it's also looking at it from supply chain management and what is that? What is the role and how does that manifest itself throughout that process and manage that from an active point of view using digital twin. Natural resources covers oil and gas, mining, but also it covers alternative resources such as water, such as solar, such as hydro, such as geothermal, all those different aspects. And you'll see an example of that coming up some of the work product within the working group there and some of the activities engaged in those areas. Infrastructure is not just about smart buildings. It also scales out to smart cities and understand the infrastructure around that. So you're talking about the bridges, the train, you're talking about the roads, you're talking about all those different aspects. And then look at it from a standpoint of traffic management and optimizing people management and transportation from that, all that overall area, transportation hubs. So pretty extensive coverage in that. That is one of our largest working groups. And then overriding all of these, not overriding, overseeing, is our organization we call the 3T, and that is terminology, taxonomy, and technology. And when I say a horizontal level of technology, think about that as being security. Security and trustworthiness. How can I understand the data that I'm seeing? That how do I know that that is something I can trust? How secure is that data? How do I ensure there's no man-in-the-middle attack that's disrupting that or putting false data through? And then, as I talked about, having that common terminology and the common vernacular. So being able to understand and speak the same language. And part of this is also that platform stack where you have a representation all the way from the convergence, as Manjeet was talking about, where the informational technologies converge with the operational, the things that turn, the things that spin, the things that move. So that's really what the 3T is all about. Next slide, please. And from that, we also look at the common characteristics relative to a digital twin. The lifeblood of a digital twin is data. You need to be able to understand and gain what is that actionable insight? What is that data telling me? So there's analytics involved. Well, I need to get access, so I have connectivity. That opens up threat thresholds. So now I have to worry about the security. As I talked about before, with the security that comes trustworthiness. And trustworthiness involves the resiliency of the data, the reliability of the data. And obviously in healthcare, very important is the privacy of the data. So you bring in data governance, those aspects. And then you need to be able to access that data. Where is it stored? How is it safely secured? So these are all the common characteristics that we look at, but then there are enabling technologies. Let's take analytics, for instance. You now have trying to understand what is that data telling me? I've captured the data, but I need to understand that. And that could be a simple dashboard. It could also be virtual reality or augmented reality. It could also be a pure stochastic approach, an algorithm. You'll see an example of that where that's being used very effectively for quality control in manufacturing. So you have all of these different common characteristics with their enabling technologies. And that's really what the 3T, what the terminology, taxonomy, and technology working group is really looking at. It looks at across the life cycle and the different phases of the digital twin. Next slide, please. And through that, as I said, you saw the platform stack there. So that convergence of the information with the operation side. And how does that look from an overall reference architecture as you stack that up? Again, that physical representation, a virtual representation of a physical entity and or process. And then look at that data flow and look at how you manage that data and the service interfaces, the applications, all those aspects. So we create this reference architecture, which gives you essentially a framework or a blueprint to then look at the different areas within the domains that we talked about, the vertical working groups, and being able to understand that, looking at it with the different lenses coming out and be able to identify where the gaps are, or there are unique areas in differentiating what's common and what's differentiating to those. So that helps, again, to provide that overall structure of what a digital twin really is and what it means in the different applications and different domains. Next slide, please. You'll see some examples coming up. Then we look at it from the standpoint of how do you define it in terms of an entity itself, an asset. So a physical asset, a single atomic entity, a discrete digital twin. But then, as you saw the example with the automotive, now you bring in other elements of that and you create a composite. So it's an assembly of these discrete digital twins, the different types of sensors, the different areas, the powertrain itself, the compute, as Manjeet was talking about it, all of those, and then combine that to create a system of systems. And that's where you get this composite. So next slide, please. And there actually is a digital twin of an entire country. And this is through the Center of Digitally Built Britain with Cambridge University, and how this can be looked at from a digital twin to provide access to the data across all the different areas that you could imagine that create not just a city, but a country itself. And the data governance, the security becomes very, very key in these areas. Next slide, please. So we talked about it in the context of automotive before in a digital twin. If you think about it, many people don't realize every single Tesla vehicle out there has a digital twin. It has the ability, it knows where the vehicle is. It understands from a modeling in terms of the performance, understands and knows what the acceleration is, what the braking is. It also has, next slide, please, what's called situational awareness and event intelligence, and being able to recognize that and understand what is happening, not just within the vehicle itself, but also outside the vehicle, and to be able to do that at any given point in time. So you can imagine all the different opportunities that opens up. In fact, there's discussion now, and it's been moved forward to, based on having that data, they know exactly when the accelerator has been pressed. They know what the speed limit is because they know exactly where that is. So that opens up an opportunity now to create an entire adjacent market of insurance. And it's been forecasted that that will bring another over $20 billion of revenue stream into Tesla because they have that knowledge and they have that actionable insight. Okay, so we look at it from the standpoint of this was actually supposed to build, but showing you from the very starts where you plan, you have your design, you have the build, and then you move forward into the commissioning and actually the deployment, the operation, the maintenance. But then you have that continual closed loop ability to now have that continual process of improvement. You're having the data in real time or in as real time as needed to then be able to identify from a predictive maintenance standpoint, are there areas that we need to address immediately? And that's where the virtual representation, your model, your simulation, your digital twin effectively can now work to then make those changes and ensure that the operation continues or that you're moving forward in a safe manner. And then you get all the way down to the point of even through the decommissioning and the retirement. Next slide, please. And so here's one of the examples I was referring to. This is a system that is a company that does multi-million-dollar CNC machines. And they are looking at it from automotive manufacturing. Here you can see a crankshaft. And the purple light there is a laser that's actually being used and applied to the crankshaft. And you see in the lower left corner a simulation model itself. So you see the digital twin of the system, and then you can see there as the image is being captured, and this is over 1,000 frames per second, that image is being captured and it's being analyzed. And you can see the algorithms, the machine learning algorithms being used, this density estimation to ensure that the laser beam has not been exposed to the crankshaft for an excessive amount of time, which would introduce anomalies in the behavior. And you can see that represented in the top left corner with the brown spotlight there. So you know that there's a potential problem there. So they're using this, combining artificial intelligence or machine learning with the digital twin for quality control. Next slide. Another example of where a digital twin factors in is in the decentralization of the grid, and look at that from a standpoint of using the repeating patterns in nature, so like a fractal, but being able to look at that to introduce high resiliency and fault isolation. So you don't have a situation where you have a central switching station that can bring down an entire state or Eastern Seaboard, which had happened many years ago. So this is a member of ours that came to us after they saw a presentation. They said, this really aligns very well with what we're doing. We're looking at agile manufacturing processes, and we're looking at following the patterns in nature from a fractal standpoint to decentralize the grid. And so that's where the company is Agile Fractal Grid. So next slide. And so what they're looking at is in the lower left corner, you can see it's not just about the source of the electricity, but it's also bringing in very, very high performance computing, very high performance and very low latency communication, as well as a very strong security enclave. So think about that concentric area as a very small area in terms of a microgrid. So taking alternative resources to generate the electricity and to have that in, say, a village or a town, or build those together now, bring those towns combined and counties combined to create a city, or you have a district now. So now you have another level of tier where the digital twin is involved in actively managing that. Then you bring those cities together and now you bring in a region. You combine those. So now there's another layer of added functionality, capability that the digital twin is playing, actively managing the transmission, the distribution of and the generation of the power. And then look at that from the regional areas. You have all these state centers now bring that all the way up into combine it to a national level. So now you add in the complete coordination and activities based on the model that you have compared to the real-time scenarios, what's happening in real time, being able to transact that. So you have multiple transactions happening. We talked about fintech. So having that at an autonomous level and dealing with all the abilities to handle those transactions and manage that at a national level. And here you can see an example with this Digital Twin Integration Center. This is exactly what's going on right now in the state of New Mexico. The state of New Mexico has stated by 2030, they will not allow any fossil fuel production for their electricity. It will be based on solar, it will be based on wind. This fractal grid is implemented and being implemented and piloted in the state of New Mexico. There's several different YouTubes. If there's interest, I can send you some links afterwards. But that is continued now. And not only is it able to use alternative resources to generate this electricity, which is now green electricity, if you think about it, but that electricity can also be used to then generate alternative fuel in the context of green hydrogen. So you can see this is a program that is being laid out right now. This is one of the, I would say, technology showcases within the Digital Twin Consortium. And we have several different active members, as you can imagine, with the scope of this. Next slide, please. Another example, now that we've gone above ground, let's take you underground. Another example of where a digital twin is being actively used and recognizing significant value is in mining. And this is one of our members who actually was approached to say, look, we have this problem. We're having all this unplanned downtime. What you're seeing there is a conveyor belt. There's 50 miles of conveyor belt underground. This is up in a very, very cold area in Canada. And they said, we keep having this unplanned downtime, and to roll a truck to get out there and to get down into that mine, it takes half a day. And then to diagnose the problem and then to come back out. So you can imagine how much time is spent just when they have a failure there. So they said, we just want to understand what's happening inside this mine. Why are we having this unplanned downtime? Our objective is to increase the amount of ore. So here you can see, and this was over a 6-month period, where they identified, once they came in, again, look at the conditions, what's happening, over 180 hours of preventable downtime. And that translates into direct results of when they cannot get the ore out of the mine. Next slide. As I said, there's over 50 miles of conveyor belts connected here, and that's transporting the ore out. It just so happens that the company that owns this mine actually owns the fertilizer plant where that ore is required to be used for fertilizer. So you can imagine when you have that kind of downtime, they're not able to sell the fertilizer. So they came to our member, and asked them, what can you do? How can you help me to identify it? And they said, we can not only help you identify, we can also help you to understand how you can actually use this and use a digital twin through the modeling to be able to predict prior to having that failure. Next slide. So as I said, over that 6-month period, you can see here, time to value, 30 days to deploy the initial release of this. integrating it, bringing this all together. They had a 30% reduction in conveyor downtime because they identified the specific area where they had the failures. They were able to model it. They modeled the conveyor belt, what was happening there. They actually put a whole series of sensors, including cameras, identifying the problems. 52 long conveyors in series, monitoring and analyzing this information every 2 seconds. You can't handle that in a spreadsheet. So they created real-time dashboards where they were able to show and monitor, and then they were able to go down and look at it from a decision support, rules, recommendations, and be able to provide this level of expert knowledge capture. But not only that, to be able to use that information and to be able to identify and define rules and recommendations based on the different thresholds of that sensing and what they were seeing, and then identifying exactly why that was happening, and actually going to the manufacturers of the equipment, and again, back to that continuous improvement loop, being able to fix that and address those issues. And you can see here what that really came down to. It was roughly savings in the tune of $4 million. And what they said was, well, if you can do that for the conveyor, what about our other systems? Let's look at our borers. Let's look at the pumps we're using. Let's look at the crushers, the fans, and even how we use data throughout our organization. And by the way, this was one conveyor belt, one mine. They extended this out across across all these equipment, and then they extended it out across the other 5+ mines that they owned. So you went from 4 to tens of millions of dollars, all the way up into hundreds of millions of dollars. And they're continuing to extend and find efficiencies using the digital twin, using those capabilities. Next slide, please. Another example, and this is in mining, but you could think of it in any manufacturing environment, is you can use the digital twin to give you the ability to optimize in real time based on your virtual representation, based on your high fidelity simulation model, but having that connection, that synchronization in real time of the data coming back to be able to do this predictive maintenance, to be able to understand. Our steering committee chair, Bill Rue, who came from GE Digital. He was the CEO for digital transformation. He is now the CEO for digital transformation at Lend-Lease, wanting to bring all those technologies forward and moving, not just wanting to, but actually realizing that and the benefits. He basically said, came out with a statement that really what the digital twin provides you is a crystal ball. You're using historical data based on current data. Remember that situational awareness, event intelligence, to simulate and predict the future. And I was just in another session where somebody was basically making the statement, yes, and we use the digital twins. We run those digital twins faster than real time. And from that, we're able to analyze many millions of what if scenarios and be able to do that and identify that so we can be prepared in any one of those cases in terms of what we may be faced with and how to have the most optimal outcome and decision made. This was actually for nuclear reactors and how they were looking at that. Another area that I had heard about was also a similar sentiment, was we're doing this in terms of water management for flood control. When we have a tsunami coming in, how are we going to control this? What are the areas? So they know down to a T what they can do, what reaction they have to take, because they have an entire digital twin of their entire water management system and all the dams and the controls and the locks and the gates. In this case also is an example of using a digital twin for doing essentially safety management and doing a safety program. So virtually you can set that up and use it from a safety program. So within
Dan, this is Steve Lundberg. Could I just interrupt you for a second? There was one
Absolutely.
question that came in that I think would be worth just
Sure.
elaborating on.
We're just
for a
about ready to
moment.
wrap it up with this next one, but go ahead, please.
Yeah. So that question is really, what's the difference between digital simulation modeling and digital twins? Or is there any difference?
Absolutely. No, a great question. And that is part of the confusion, because people say, well, is my simulation model, is that a digital twin? The answer is, where is the twin? If you have a model, the twin is really giving you the ability, again, that virtual representation of a physical entity and or process that has the synchronization of the data coming back. So the data is the key. We've seen this in many different instances where, yes, you can have a model that you have represented and a high level of fidelity, but what happens if you have a scenario you haven't considered? And you can see these parameters coming back through the data in a continuous, what we call our real time, or whatever the frequency is, requisite frequency is, to be able to represent that. So then you now have that information and you say, wow, I had not even considered that situation. Now I have the data that's telling me exactly what's happening from an environmental standpoint. I can use that data and I can run my twin faster than real time and see what that outcome is, and maybe come up with something that I can deal with as far as how to either mitigate a circumstance that I have or to optimize what I'm doing. An example of that would be a blast furnace. A blast furnace is running. You have all the information about the metallurgy. You have the information about what's coming on, but the slag and the production of that is continual. And you need to be able to have these tap routes to be able to get the ore at the most purity level you can. So while you're doing this, all these different situations are coming in play. In real time, you're running that model based on the real environmental data that you're getting directly from the sensors, and being able to continue to change that dynamically, because the level is always changing within that area. And we have a member that's doing exactly that. A simulation model would be great. It is great, but it only goes so far. As soon as you connect the real-time data to it, now you get that overall holistic view that you wouldn't be able to get. I hope that
So
answers your
there's another question here which relates to that. I think you can tie it together. So someone
Sure.
else said, well, is like Waze or Google Maps created a digital twin of traffic flows when, it shows you in real time what traffic is flowing. But I think what you might say is that it doesn't do anything with that data in order to affect traffic flow. Or what's your thought on that?
That's exactly right. The person who's getting that information is the one that's taking that action. The other part of that, and I think Manjeet touched on this also, about the automatic nature of what's going to be happening here, where the digital twins are going to be communicating and transacting between themselves, independent of having the human in the loop, so to speak. And we're already starting to see that coming through in some of the financial areas. And that's one of the principles also being looked at in terms of this area here, where I talked about that decentralization as a grid. The first area that's manifesting is really in batteries, in buildings as a battery. And they're looking at how can we make that most efficient? And then from that, how can we reduce our carbon footprint? And as a result of that, get carbon credits, which actually will come back in terms of benefits to the owners. I don't know if you're aware, but New York City has enacted, as others are following, very strict carbon footprint limits, let's say, and they're penalizing owners if they exceed those. So this is one of the areas where we're looking at this as a pilot example of how we might be able to address that, and other benefits that come as a result of that. And this is where, again, with the consortium, bringing that breadth and depth of experience and knowledge, bringing that together through the collaboration and best practices. And that's what we have, as we call these technology showcase projects, involving several of the members and bringing them all together and being able to highlight the value and the advantages of a digital twin. And we're seeing this being recognized in many, many different applications and markets. Next slide, please. So I appreciate, again, all your time, and there is a tremendous amount of opportunity, and what our members seeing is the opportunity not only to influence, but also to innovate, to collaborate and develop through these technology showcases and demonstrate their thought leadership. So with that, if you want to learn more, I encourage you to take a look at our website. So thank you again for the opportunity to present.
Thanks, Dan. That was fantastic. And then we'll move on to Steve Komarec to bring it on in home.
Sure. Thanks, Steve. Thanks, Dan. Yeah, so I'll just jump right into these slides. I worked with our patent analytics department here at Schwegman just to generate some high-level statistics that examine what kind of patent filings have been going on related to digital twins. So we did a search that just includes the phrase digital twin or digital twins anywhere in the patent application for US applications. And we turned up, as you can see there, about 1,300 patent references. And I think for a point of reference, we did the exact same search for some other technology phrases or catchwords. And if you do the same search for virtual reality, there's over 113,000 references. For Internet of Things, there's 70,000 references. And UAV or unmanned aerial vehicles, there's about 15,000 references. And then on the opposite end of the spectrum, if you search for metaverse, there's only 316 references. So you kind of see we're in the early stages of patent filings. And so this is a plot of the references from the previous slide with the, as you can see there, prior to year, filing year, and grant year. The thing to note on this graph is that pretty much everything before 2012 is just noise in the digital twin search, errors or priority errors or CIP. And it's not until 2012 where you see the 2012 timeframe where you see digital twin at least being referenced in the specification in the context we've been using here. And then in the 2014-15 timeframe, you actually start to see it in the claims. But I guess the point of this slide is that you really see filing of patent applications take off in about 2015. So next slide. This is just a similar graphic showing granted patents claiming digital twin. And again, you can see in the very recent past in 2019 and 2020, you see a big uptick in granted patents claiming digital twins. So next slide. This is the patent assignees for the 1,300 references, applications, and granted patents. And I think what you can see here is just that it's a small universe of patents we're dealing with, and it's the early adopters really have the foothold in the patent filings for these. And you can also see names on here that you're familiar with, or even ones that are members of Dan's consortium. And also you see companies that get at the type of companies that would do digital twinning that Dr. Rege talked about, companies like Siemens and Johnson Controls and General Electric that are doing physically large projects, complex projects, and manufacturing operations. So next slide. This is just the same graphic for granted patents. And again, it just highlights the small number of patents and those being concentrated in an even small number of owners.
Steve, I have one quick question. Is this data only for US companies or is this worldwide? It looks kind of.
Yes, it's just US. This slide right here is US grants. The 1,300 number is US, any US publication or grant.
Right, but it could be an international company, but only their US filings.
Absolutely, yes, there are numerous other PCT or EPO patent filings, but in order to just bring the universe down to something, that we can do a little bit of meaningful analytics on, we just kept it to a smaller universe.
Okay.
So on the next couple slides, I just looked at the patent classifications that the patents mentioning digital twin are in. And if we look at the next slide, I'm not going to read it, but from these patent classifications, we can kind of see the subject matter that the patents relate to, and some of the phrases or words in these categories that stuck out to me that relate back to what Dan and Dr. Rege were talking about are forecasting, computer-aided design, estimating useful life, healthcare informatics, repair or maintenance, machine learning in modeling and simulation. So next slide. Again, this was just, this is now not, the previous slide was just the first category, which is usually the broadest description of the technology. This slide is all categories that were applied to the patent applications. So you can go to the next slide, and it really is repeating some of the categories from the previous slide, but there's a little bit more detail, and you can see categories that relate to smart factories for reducing greenhouse gas emissions, or smart factories for scheduling and planning, as well as computer systems based on biological models. So this is prosecution analytics, or relates to information about what the patent examiners were saying about these applications. And I won't go into great detail on this, but a couple of things that jumped out to me are that these applications are facing patentable subject matter rejections, which is nothing new in the patent world, but just something to be aware of as you're drafting and filing applications. And actually in the blue chart, we can see that a fair number of applications are allowed on their first on the first action from the patent office, or after only one office action. So to me, that says there's not a lot of prior art, and it's possible to get applications, at least ones that have been filed so far, through the patent office quickly.
So Steve, I just want to interrupt you there for a second, but looking at the data, just to point out to people that the last couple of years, there's only partial data because of we can only see published applications. So it looks like it's trending down, but actually that's misleading, because the last 2020 and 2021 are only partial years worth of data.
Yes, that's a great point, Steve. Thanks for pointing that out, especially to the non-patent people here. So yeah, this is just an automatically generated graphic from the patent search software that's picking up on words repeated in these patent applications. And the thing that was interesting to me in this is just looking at the most frequently used words in the inner ring there. It almost reads like a pseudo claim or a template for a claim that you would put in a patent application. And it really is getting at what a digital twin is, where you have sensor data from a real world asset. And then from that data, you can generate an image and control something at a user interface. And in fact, in the last few slides that I have are just some examples of real world patent applications. I tried to find a patent application from each of the use cases that Dr. Rege talked about. And then the first one is a manufacturing use case where you can use a digital twin to check for assembly of two parts to create a larger assembly. And if you go to the next slide, you can see that that same pattern, kind of that infographic was related to of a real world asset, a sensor taking data from the real world asset, and then creating or updating a digital twin. And then maybe something that's particular to the patent world, but useful in any event, is providing some type of real world update. And in this one, you provide a corrective information to the person doing the assembling if the digital twin doesn't match up to the real world case. So then the next slide is an automotive case, and this is this application relates to predictive maintenance reports. This is a Toyota application that hasn't granted yet, but if you look at the claim on the next slide, again, you can see the real world asset or a digital twin, and then a sensor to get data from a vehicle, doing simulation, and then generating some type of real world output of an electronic report that can predict when a failure might happen. And then just to the last one is a healthcare example. And I think if you just look at the claim, you can see it involves, I guess you can't see, the boxes are off a little bit, but yeah, you can see just the use of a healthcare tracker on a patient that can feed information into a machine learning engine and then output data. And in this case, the data can be used to facilitate scheduling an appointment with a clinician. So that was, that's the sum of the analytics there. And so just high level things to consider. As I mentioned, patentable subject matter rejections, which are not expected when you're dealing with computer implemented inventions. And I think that's something that can be addressed as long as you're aware of it going into the drafting process. And then infringement detection, will you be able to detect infringement if you have the twin in a separate place from the actual real world entity? And then again, infringement assertion, if you have a twin in one location being operated by someone and a real world asset being operated by someone else, who are you going to sue? And then as Dan mentioned, standards and compatibility is going to be an issue with digital twins. So that's something to be aware of in the patent world as well. So that was what I had.
Hey, thanks so much, Steve. Hey, just time for, we're run over, but I want to just stretch this out a little bit. There's quite a few questions that kind of relate to the difference between digital twins that are modeling physical entities or physical processes versus ones that are like marketing digital twins. And then there was another theme, which was sort of like, if you buy an Apple Watch and they're monitoring your blood pressure and your heart rate and whatever else they'll eventually monitor, are they constructing a digital twin in a sense of your physiology? Any answers to that from either of the two technical experts? I'd appreciate it.
Sure, I can take a stab at some of that. So as far as marketing aspects are concerned, I wouldn't call them the applications of a digital twin, but it would be building a recommendation system, because you're not really building a model of an individual consumer's behavior. You're building an aggregate model of everybody's similar behavior. So a person who watches one type of a movie will recommend something else based on marketing. So that uses machine learning, which is also used in the creation of a digital twin. So applications of machine learning, I would say, to marketing. The other question you mentioned about the usage of a twin in the creation of a physical object like a Apple Watch, for example. So in that case, a twin would be used in the designing of that particular product in the sense of performance, battery usage. So if we do change the design of that particular Apple Watch in a particular manner, if we make it smaller, if we change the display, how would that affect the performance overall? That is where the twin would be used. I'll let Dan add to that as well.
Yeah, and I think again it gets back to the connectedness, the data coming back. So there's the development stage, and if you think about it, the life cycle that I was showing earlier of that digital twin, where used for the development or the early planning stages and understanding and doing virtual validation, let's say, of what your thoughts were, and then based on that, going out and then building your physical entity, and then actually having that go operational and being able to go from there and look at it from operational into that maintenance stage, where the digital twin is very active in monitoring that and the thresholds, depending on what the designers and the subject experts are looking at. One of our members actually has a platform where they enable, it's a no-code platform, so it's literally drag and drop, to build a digital twin and to be able to then allow the the subject matter expert to set the recommendations and to set the effectively use the rules engine to identify the specific areas that they know where they're most likely, based on their years and years of experience, way would expect to see things, anomalous behavior, and being able to use different areas to then identify that and then figure out how they can use that information to then bring more, optimize the outputs, increase the productivity, the efficiency, all these different examples. So you need to look at it across the entire life cycle and the advantages at each one of those instances that a digital twin can provide. I think one of the other examples was a virtual representation of a process. One of those examples would be supply chain management, and being able to understand and holistically take all the different parameters, all the different information in, to be able to ensure that the supply chain can meet the objectives and the deliveries of the specific areas. One of our members handles, if you think about it, I hadn't really thought about this in this context, but they handle 80%, one of the companies that they're working with handles 80% of the oxygen canisters that deliver to 80% of the world, the world's hospitals. You can imagine, and we've already seen what happens, unfortunately, when that supply chain, something so critical, breaks down. So being able to have an understanding of all the aspects, the manufacturing, are there enough canisters? Can we get the production that we need to fill those canisters? Understand what the delivery routes need to be to get to those out to the different hospitals. Understand now, look at it from that standpoint. What is the usage? And all of a sudden you're seeing a spike. And now what happens? You have these shortages. Can I reroute some of this, some of these canisters, or some of the materials that I need to be able to produce the canisters? Can I reroute to ensure that I can meet those supply chain requirements? So that's an example of taking in just a massive, massive database and being able to correlate that and understand the relationships and the impacts in the context of as you're doing the operations based on the data that's coming back to you. So I think that's another good example of how a digital twin is being used from more of that virtual representation as opposed to a physical area.
Well, thank you very much, Dan. Much appreciated. Manjeet, Steve, of course, Suneel, you guys did a great job. We're going to have to wrap it up, of course. So we want to thank everyone for attending, and we'll hand it back over to Michelle to finish up. Thank you.
Thank you for joining us, everyone, and thank you to our speakers. And we invite you to come back on September 28th for a webinar about inventorship and assignment, and next month for the final episode of the Practical Patent Practice webinar series. Thank you again for joining us, and be well.